Welcome to this explainer. Today, we're basically putting on our cosmic detective hats. We're diving headfirst into what scientists call the absolute deepest, most profound unresolved mystery in modern theoretical physics. I'm talking about the black hole information paradox. It's a puzzle that has literally confounded the most brilliant minds on Earth for half a century. And together, we're going to unpack exactly why this mystery is so absolutely pivotal to our understanding of reality itself.
To really grasp the immense stakes of our mystery, just imagine this. What actually happens to the information inside a book if it's thrown into a black hole? The renowned physicist Leonard Susskind used this famous burning book analogy, and it makes a brilliant point. Think about it. If you toss a book into a regular campfire, yeah, it burns up. But theoretically, if you had a powerful enough supercomputer, you could track every single molecule of smoke, every tiny flake of ash, and literally reconstruct the words printed on those pages. The physical item is gone, sure, but the information, it survives. But if you throw that exact same book into a black hole, does the universe truly permanently erase it?
Okay, let's dive into this, because to understand why erasing that book is such a massive cosmic crime, we have to look at a fundamental rule of quantum mechanics. It's called unitarity. Basically, this rule dictates that information simply cannot be created or destroyed. It preserves all the possibilities of a quantum state over time. And this is backed up by something called the no-hiding theorem, which essentially tells us that if information seems lost, well, it's actually just hiding somewhere else in the universe. You know, this isn't just a casual suggestion. It is an absolutely unbreakable law of how our universe operates.
And honestly, that brings us right to the core conflict of our explainer. We're looking at a heavyweight clash between the two undisputed pillars of modern physics. In one corner, we have Albert Einstein's general relativity. It predicts that once information falls past a black hole's event horizon, that's it. It's lost forever, totally trapped in the crushing gravity. But in the other corner, we have quantum mechanics, which insists that information absolutely cannot be destroyed under unitary evolution. Pitting these two giants against each other, well, that is exactly what creates our paradox.
So, let's examine the scene of the crime, the event horizon. In classical physics, this is the literal point of no return. The gravitational pull gets so insanely intense that not even light can escape it. According to the classical no-hair theorem, this boundary acts like a perfect mask for everything inside. To an outside observer, the black hole is completely featureless. It really only keeps three properties of whatever formed it: mass, electric charge, and spin. That's the whole shebang. So whether a black hole is formed by a collapsing star or just a giant massive cloud of neutrinos, from the outside they look totally identical. The hair, all those unique informational details, is seemingly just gone.
But the plot thickened big time back in 1974 when Stephen Hawking made this absolutely brilliant mathematical discovery. He realized the event horizon isn't entirely black. Hawking showed that quantum fluctuations actually cause virtual particle-antiparticle pairs to just pop into existence right at the edge of the horizon. The intense gravity pulls one negative energy particle in, while the other manages to escape into space as real, positive energy. We call this Hawking radiation. Over an incredibly long time, this process causes the black hole to gradually lose mass and eventually it just evaporates completely. But here is the paradox. This radiation is purely random thermal energy. It carries exactly zero information about the stuff that originally fell in. So when the black hole eventually evaporates into absolutely nothing, the original information is completely, irretrievably destroyed. No way around it.
Let's move to and see how this builds, because to really understand this mystery, we have to look at how it evolved over the last half century. It all started in the 1970s when Jacob Bekenstein and Stephen Hawking defined black hole entropy and discovered that super problematic radiation. Then, zooming into the 1990s, string theorists proposed the holographic principle to try and somehow save the information. By 2012, a highly controversial idea known as the firewall paradox ignited fierce debate. It suggested a violent boundary of energy just burns up information right at the horizon. And finally, hitting 2019 and 2020, we saw some truly game-changing breakthroughs with page curve calculations and replica wormholes.
So, who are the primary suspects here? What are the leading theories physicists have proposed to track down this missing information? Well, there are a few fascinating ideas, but they all come with major shortcomings. First up, fuzzballs. This suggests black holes have a stringy, complex structure, but it requires some pretty exotic branches of string theory to actually work. Then we have firewalls, which propose a high-energy boundary that burns things up before they even enter.
The problem? That totally violates Einstein's equivalence principle, the core idea that a free-falling observer shouldn't feel anything special at the horizon. Finally, there's holography. It suggests information is encoded right on the surface, but at first glance, that appears to violate a strict quantum rule that forbids copying information.
Let's look slightly closer at that first suspect. The fuzzball theory, which, by the way, is a delightfully unintimidating name for something so massive, proposes that black holes don't actually have a central point of infinite density. No singularity, not even a sharp empty event horizon. Instead, they possess this highly complex, stringy structure that extends all the way out to the edge. By giving the black hole this messy hair, or physical structure, rather than just an empty vacuum, the information of infalling matter actually has something to interact with, so it's not just lost down a bottomless pit.
Now, what's really interesting about this slide is this radically different approach called holographic duality. Pioneered by Nobel laureate Gerard de Hooft and Leonard Susskind, this suggests that our 3D universe might not fundamentally be three-dimensional at all. Wild, right? Instead, it could just be a projection of information encoded on a distant two-dimensional surface. It's kind of like a standard hologram you'd see on a credit card, a completely flat 2D surface that somehow contains all the data needed to construct a fully 3D image.
When applying this holographic idea directly to our paradox, Susskind suggested a truly mind-bending reality. He said, and I quote, "The information about matter falling into a black hole isn't lost. It's encoded on the event horizon, much like data on a hard drive. In this model, the black hole's boundary acts like a sort of stretched horizon. The information from our fallen book gets totally smeared and duplicated right across this 2D surface. So when the black hole eventually emits that Hawking radiation, it isn't truly random anymore. It's actually a heavily scrambled version of that original information being carried right back out into the universe."
But wait a second. If the information falls inside the black hole and is also plastered on the outside horizon, doesn't that mean the information was literally copied? Quantum mechanics strictly forbids the cloning of information. You just can't do it. To fix this glaring issue, physicists proposed black hole complementarity. Basically, it's all about perspective. One copy of the information is seen by an observer falling in. The other copy is encoded on the horizon, but that's visible only to an outside observer. Because no single observer can ever communicate with the other to compare notes and see both copies simultaneously, the no-cloning theorem is completely safe. The quantum laws are mathematically preserved.
This intense debate over firewalls, fuzzballs, and holograms raged on for decades. It was a real stalemate. But then, we hit the year 2019. This year, stretching right into 2020, marked the moment of a massive, absolute game-changer of a theoretical breakthrough. It completely changed how scientists view the information paradox today.
It all comes down to this really brilliant concept, the Page curve. Named after the physicist Don Page, this curve is essentially a graph that maps the entanglement entropy of a black hole as it evaporates. Think of it like this. If information is indeed conserved and eventually escapes, the entropy of the Hawking radiation should initially rise as the black hole evaporates. Then, it should peak about halfway through at what's called the Page time, and eventually fall right back down to zero when the black hole is completely gone. For decades, nobody could prove how this could actually happen. But in 2019, scientists finally calculated this exact trajectory mathematically. They proved, for sure, that the information must somehow be escaping.
So how did they finally prove it? By utilizing some truly bleeding-edge mathematics known as replica wormholes. Now hold on, these aren't the sci-fi wormholes you can fly a spaceship through. They are extremely complex gravitational saddles, essentially advanced mathematical shortcuts used to calculate quantum possibilities. When scientists calculate the entropy of the radiation, these mathematical wormholes connect the interiors of multiple simulated copies of the black hole, and they reveal an intricate, hidden entanglement linking the inside of the black hole directly to the radiation sitting outside.
So, the crucial point is that these replica wormholes lead us to something called the island formula. Here is exactly how it plays out. First, Hawking radiation collects far away from the black hole. Second, due to those mathematical wormhole connections, a mysterious island of quantum information forms deep inside the black hole's interior. And finally, the information within this interior island becomes mathematically linked to the radiation outside. This means the information that fell behind the horizon isn't actually lost at all. Thanks to this island, it's secretly been part of the outgoing radiation all along. This is potentially the ultimate key to cracking the whole case.
Now, you might be wondering, why does all this dense cosmic math actually matter to us down here on Earth? Well, and this brilliantly illustrates the point. Solving this paradox is about so much more than just a quirky space riddle. The quest for quantum gravity forces us to re-examine the very foundations of reality itself.
It's yielding incredible new insights into quantum entanglement, which, by the way, can directly impact our ability to build super powerful quantum computers. Furthermore, it suggests that information isn't just some passive record of things, it's an active, fundamental ingredient woven right into the fabric of reality. Solving this paradox is absolutely essential if we ever want to unify the micro laws of the quantum world with the macro laws of gravity.
Which brings us to our final lingering thought for this explainer. Could the solution to the black hole information paradox finally reveal the true, fundamental nature of space, time, and the universe? We are standing right on the edge of a scientific revolution, watching the rigid boundary between Einstein's general relativity and quantum mechanics actually begin to blur. The answer is out there. It's perhaps encoded in the very geometry of the cosmos, just waiting for us to decode it. Thank you so much for joining me on this deep dive into the unknown. Keep exploring and absolutely keep your curiosity hungry.